So let me welcome you for the second session of the workshop, and we are going to continue in the anti-kaon physics. The first speaker is Albert Feijo, who is now in IFIC in Madrid. Sorry, not in Madrid, in Valencia. So Albert, please, tell us something.
First of all, I would like to thank the organizers for this invitation. Today I'm talking about new insights on lambda 1405 from Triangle Singularity for these reactions. This is quite fresh work. It has been submitted to archive very recently, and it has been carried out in collaboration with Raquel Molina, Eulogio Osset, and Daily Angram. We study the K-deuteron going to proton sigma minus and its time reversal reactions close to threshold for the first time. And this is a reaction of particular interest, not only because it's a process driven by a triangle singularity, but also because this reaction acts as a window to k-bar n subthreshold amplitudes. To contextualize and to see why this second point is so important, let me say something about k-bar n interaction. Well, this interaction is governed by the strong force, and as it is well known, perturbative quantum chromodynamics fails in order to treat low energy hadron interaction. This brings us to chiral perturbation theory, which is an effective theory with hadrons as degrees of freedom, which respects the same symmetries as QCD. The validity of this theory is limited to a small range of energies above threshold and far from any resonance. But it is not so straightforward, because the interaction between k-bar mesons and nucleons is dominated by the presence of lambda 1405, so we need a non-perturbative resummation. In fact, back in 1995, Kaiser, Siegel, and Weiser reformulated the problem in terms of a unitary extension of KPT in coupled channels. This scheme allows one to generate dynamically resonances and bound states, and this theoretical breakthrough was kind of revolution. It sparks a lot of activity in the field. Proof of that are all these papers here. Maybe I have forgotten some of them. Let me apologize for this. But the important thing is that in general, all of them reach a very good agreement with, in order to describe the k-bar n scattering data, and all of them reproduce the two-pole structure of the lambda 1405. More recently, the eruption of new experimental advances has renewed the interest on this topic. I am talking about the pi sigma invariant mass from this kind of photo production processes provided by the class collaboration, and the measurement of the shift and width of the first state of the kaonic hydrogen by Siddhartha collaboration, which establishes the K-P scattering length within a precision of 20%, therefore settling the previous dispute between Keck and Deer. So if we take some of these, let me call them the new generation models, or these newly developed models, and we check what they once they try to reproduce the scattering data, we see that looking at their cross sections, that they reach a fairly well agreement with experimental data. You see here you have the K-P going to pi sigma channels and pi lambda, and also K-P going to k-bar n, so the classical ones. So in general, these models work quite well for this issue. And also, if we twist a little bit the approach and we check what happens at high energies, we also find reasonable good agreement with the experimental data as well. On Friday, Angel is going to talk about this. Let me remind you that all this data, of course, has been used in the fitting procedures. But moreover, if we check what some of these models can reach when they evaluate the branching ratios here defined and the scattering length, the pattern is repeated. So we see that the level of accuracy in order to reproduce these values is very similar, maybe a little bit larger when we check the scattering length, but again, it's the same. All models work well in order to reproduce all this data. By the way, these observables at threshold are also included in most of the cases, or I would say in all of them, in the fitting procedures. But when we pay attention to what happens to for instance, the K-P scattering amplitudes, and we focus particularly at energies below threshold, here in the left-hand panel, we have the real part, and the right-hand panel, we have the imaginary part, and we check, as I was saying, what happens at energies below threshold. We see that there are big discrepancies in the strength of this amplitude, and as you go towards higher energies, particularly at threshold, because we have data constraining these models, and also as an evidence of what I was saying, you see how nicely most of the models how nicely converge, yeah, as you go to higher energies. Then another proof of the lack of information we have about K-bar and subthreshold interaction is the uncertainties associated to the lower mass pole of the lambda 1405. Yeah, I don't want to extend myself much because Alex has been talking thoroughly about this, but just let me say that the higher mass pole is well pinned down, while the other pole is, yeah, that if we plot the values obtained by the different models in literature, we see that all of them are scattered around the complex plane. So these last years, many efforts have been made in order to improve the situation. And in order to give a couple of examples that reflect the kind of work we can do in order to constrain or to restack information, either by fitting directly to the subthreshold data or by means of extrapolating some information from any observable. I include these two examples. The first one is this fit to the pi sigma invariant mass from photo production experiments, and then here Eulogio and Luis use a model independent fit, well, and so on. They describe the two poles in a reasonable way. I would say quite well. And then there is this value of the absolute value of this the K minus neutron going to pi minus lambda amplitude, which was extrapolated from the K minus absorption on helium-4 by people from Amadeus, and here you see that it's compared to the predictions of several theoretical models. Well, what I wanted to say is that in this line, the study we present here could shed some light in order to help to understand what is going on and K-bar and subthreshold amplitude. So the proton sigma minus going to K minus D reaction proceeds via these two mechanisms, which consist basically in triangular topologies, where here, for instance, we have a proton which interacts with a sigma minus by means of exchanging an anti-kaon. Then in the upper branch, we have a lambda star in this lambda 1405, which gives an outgoing K- and a proton, which fuses with a neutron propagating along the bottom branch to finally give the deuteron. Similarly for this topology, but instead of interchanging a kaon, they interchange a pion. Regarding the amplitude, we use in order to build it, we employ the usual elements. We see here the couplings to the lambda 1405, then the vertex, the propagator related to the meson, then the other three propagators related to the intermediate baryons, and this Heaviside theta function, which accounts for the deuteron wave function. It's worth mentioning that if one wants to see which is the role or to see what you can obtain if you include the two states of the lambda 1405, we should add a second piece like this one, but with the corresponding values of the mass and width and the couplings. So once you integrate this over Q0 by means of Cauchy theorem, what you get as the amplitude of the amplitude at the end looks like this, where we have additionally include the form factor, and then this capital V and capital W stands for the spin transition matrices, and here this integrand is defined like this. But here the important thing is that once in every blue moon, well, because it's quite rare, it's not, what I wanted to say is that it's not common, a triangle topology can develop a triangle singularity. And the conditions for this should be this one. So this topology should lie on this kind of Feynman diagrams where you have a particle A, which decays in a particle 1 and particle 2. At the same time, this particle 1 decays in a particle B and a particle 3, which merges with particle 2 to finally give C. But it should be fulfilled that the three particles are simultaneously placed on shell and they are collinear, fulfilling the Norton-Coleman theorem, meaning that particle 1, 2, and 3 in the A res frame should be collinear, and particularly particle 2 and 3 should move in the same direction, but particle 3 should be faster than particle 2 to reach particle 2 in order to make possible the fusion to generate particle C. So all these dynamical conditions are encoded in this very easy equation. Eulogio explains this in a very pedagogical way. I'm not going to enter into this because I am a newcomer in the business, so I prefer to do in the easiest possible way. So what else? Then, since what we want is to compare with experimental data, and the feasible experiment should be by means of this reaction. What we need to calculate is the differential cross-section of this process. Well, it's a normal expression for this, where these summation symbols run over all possible spin configurations. Since we have had the initial state two 1/2 baryons, we have 4 possible configurations, and at the end, since the spin of the deuteron is well determined, so we can only go to any of these states of the triplet. Well, in addition, in order to calculate the cross section, we need the couplings and the masses of the states related to, well, the couple of states related to lambda 1405, and in this case we take the ones from I would say my particular Bible, José Ramos model. Okay, first we plot which is the contribution of several spin transitions to the K-D pi sigma minus cross section. What we see is that the non-spin flip transitions are the ones which are favoring this process, as can be clearly seen from this dashed red line and this dot line. What is shocking, at least to me, is that how the spin flip processes contribute in a very poorly way. Okay, so what else? Then we check which is the role played by the contributions of each brake Wigner or equivalently the high mass pole and the low mass pole in the total cross section. If, well, we can compute both directly, and then we have this blue line, which is a consequence of destructive interference between these two guys, where we clearly see that the high mass pole offers the largest contribution, and also showing this tiny peak, few MeVs above K-D threshold, and also when these destructive interference occur, this peak ends completely masked. Then we see this panel, this left-hand panel, where we study which is the role of each mechanism, and yeah, we clearly see at naked, it's clear, evident that the mechanism B, the one which involves the interchange of a pion, is the dominant one, yeah, by far, and well, once we take both into account, constructive interference occur, and then there is an increment of 10%, yeah, for the total cross section. Okay, sorry. Okay, once we have a taste of what is happening to the total cross section, in order to make this calculation more formal or even more accurate, we replace our formalism or our wave function by the one developed by Maglite, yeah, well, which is, well, by means of using the bond model. The same here, instead of using the braid Wigners, we are going to use the theoretical amplitudes calculated from any of, well, as you will see, from theoretical approaches from chiral Lagrangians. Okay, this is a very illustrative figure. We have represented here the amplitude of the K- deuteron going to proton sigma minus process, and in this right hand panel we have the K minus P going to pi plus sigma minus amplitude. Before starting, I would like to mention that for simplicity, we have limited this calculation for the dominant spin transition and only for mechanism B in order to hide the visualization of the amplitude. So the first thing, if we start analyzing this amplitude, particularly the imaginary part, we see a smooth peak, that the imaginary part develops a smooth peak, which peaks where the triangular singularity predicts. It was around 2380, and then also the real part, it largely contributes to the amplitude, especially close to threshold where it develops a cusp. Then the interesting thing is that when we compare both amplitudes, we see that we clearly see that this guy is not a mapping of these other guys. So making clear that the triangular singularity has created its own structure. But I would like to say that if we check the amplitudes carefully, we see that okay, it's not a mapping, but somehow there is still an existent proportionality, because for instance, we are dealing with this guy. This first part, it was a prediction from Eulogio, and then it was confirmed numerically that these guys only contribute between a 5% and 10%. So the proportionality becomes from this piece here. But we have to bear in mind that this part should be integrated. Yeah. So this is going to change according to different values of the invariant mass and so on. But one should bear in mind that the part which contributes the most comes from this region where the triangular singularity is more important. So meaning that these amplitudes is gonna take values below threshold. So this leads us to believe that somehow we can extract information from this subthreshold region by means of studying this reaction. With this in mind, what we do is we compare different theoretical models by means of just swapping the amplitudes in the formula and plot the total cross section. Okay, just by checking the plot, the most eye-catching feature is the large difference in the strength once we deal with different models. Well, this is not the case for when we compare our model, Barcelona model, with Osen Ramos, but we check. So sorry, Daniel, did you say anything?
No. I just unmuted because you have 3 minutes left. So go on. Sorry.
Okay, so then when we compare any of these with the other, we see that there is a 40% difference in the case of Roca Osset and almost 100% difference in the strength when we compare with the model of Shapley-Feijo. Let me make the most of the situation to thank Alex Shapley for providing us all the inputs we need for this study. So let me finish by the conclusions. We have studied the K minus D going to pi sigma minus and its inverse reaction by a triangular topology. We have seen that it proceeds via 2 mechanisms that embeds a triangular singularity. So the peak associated to the triangular singularity shows up few MEVs, as we have seen, above K minus D threshold, being clearly visible in the case of the narrow high mass lambda 1405 state. The mechanism, then we have seen that the mechanism involving the pion exchange has shown to be the dominant one by far. And we have seen that the particular dependence, and this is the most important part of the K minus deuteron going to proton sigma minus transition on the K bar and amplitudes below threshold, weighted by the structures tied to triangular singularities, makes this process very sensitive to different models. So, and this is the big statement here, the measurement of this reaction will provide valuable information for the K bar-bound states in nuclei, as well as it will help to narrow the uncertainty around the location of the lower mass pole of the lambda 1405. So that's all. Thank you very much for your attention.
Okay, thank you, Albert, for sharing these fresh results. So are there any questions? We have a time for maybe one. Yeah, so there is a...
Can I start?
Yeah, sure. Yeah,
Daniel?
I think
okay. This is Angels. Thank you, Albert. This is a very nice talk and very interesting work. And I think that the fact that you also find the difference between using simple brightening shapes or the full T matrices, this also gives you a difference. It is also another indication that the subthreshold, that you are sensitive with these reactions to the subthreshold amplitudes. So the question, actually, I don't have a question. Maybe it's for the experimentalist. How is it? Is this a feasible experiment? Is Amadeus able to measure that, or Siddhartha, or other places in Japan? Maybe the experimentalist can answer. Thank you.
Gracias, Angels.
I don't see anybody who would like to respond.
Laura, we don't hear you.
Okay,
So maybe Laura.
yeah, so I have a question about the couple channel, because at the very beginning of your talk, you were showing scattering experiments, and then you were also showing how in the calculation you do,
Could you please speak louder, Laura, please, because I cannot hear you.
Okay, I'm sorry. Is it now better?
Yeah, slightly better, but better. Thank you. What were you saying? Excuse me.
So basically, sorry, can you hear me now? Because I did.
Yes.
Okay. Okay, so I wanted to ask you about the constraint for couple channels coming from scattering experiments, elastic and inelastic scattering. You showed it exactly here. Now, these errors, that I see here in the evaluation of Rn and Rc, these errors seems to me very small if I look at the errors of the scattering data. So, and I was a little bit wondering.
Well, I don't know what other people does. Well, I know what, for instance, Oyer does. It's the same that we did, and what it's simply that we vary and the parameters we have in the model within 1 sigma, and then this is what we get when we reproduce these values.
Okay, but can you go back to the because I mean my question it's now let's say motivated by the fact that I wonder whether by looking at the K-P final state in femtoscopy at the LHC, where we have all these initial states present, because we can have K0n or pi sigma that then goes to K- proton, you know, and this will modify the correlation function. I'm wondering whether these, let's say, LHC data can help constraining these coupling parameters better. Because this is really not clear to me, because every time, I mean, I hear about the constraint based on scattering data, I always hear that this coupling, let's say, constant or this ratio that you showed are well constrained. But then I think that what you tell me is that if you vary your models by 1 sigma, you still reproduce very well the data because the error of the data is very large, right? I mean, go back to the figure, maybe because I'm not maybe explaining myself. Go back to the previous slide. Okay, imagine I make it for an example. Imagine that the error is here. So can you see my yeah? Imagine that the error on this data would be factor 10 smaller. Yeah. Would these or same here? Okay, same here. Yeah. Would this help in any way or constrain in any way better the calculation that you are doing?
Yes.
So this would be relevant, you tell me.
Yes.
Okay.
Yes, sure. Yeah.
Okay.
Would be great.
Okay.
And this Magda will report later. When is your talk, Magda, scheduled? Let me check.
Okay, yeah, there
It's
was
just
also
next one, yes. So on very recent results on sigma 0, lambda pi 0 scattering, Magda will tell us.
Christian, are you talking to me? I have problems to hear you.
yeah, we are.
Also me, I'm sorry. Can you hear
okay,
me better
maybe
now?
we can.
Okay, nothing. I was just adding that on this, Magda will soon tell something.
Okay, great.
Yeah, there is also a comment from Masai Wasaki in the chat. So maybe Albert, you can respond in the chat, or we can discuss later. But let's move for the next talk.
Let me answer.
Yeah.
Thank you, Daniel.
Okay.
For letting
No,
me know.
thank you for. Yeah, thank you. It was,
Thank you.
Yeah, nice, new, exciting. Thank you. Okay, so yeah. So the next speaker is Magda.
Yes, thank you. Let me share my screen.
Yeah. Okay, she is going to update us about the Amadeus experiment.
Okay,
so
can you see my presentation?
Yes. Yeah, it's not full screen, but I can see that.
Ah, okay. Now?
Yeah, perfect.
Okay.
Okay.
At the beginning, I would like to thank organizers for inviting me to this very nice workshop. I'm going to speak about the status of Amadeus studies of low energy chaos interaction in the nuclear matter. And this is the plan of my presentation. So at the beginning, I will tell about the motivation and the scientific case. Then I would like to describe the Amadeus experiment at Daphne and show you the main recent analysis results. And at the end, I will conclude. Okay, so motivation of our studies is to investigate K-bar N interaction in nuclear matter, which is fundamental for quantitative studies of non-perturbative QCD in the STRANGeness sector. And as we know, chiral perturbation theory successfully describes the pion-nucleon case. However, it cannot be applied in the sector with the strange quark because we have two broad resonances which appear just below the K-bar N threshold. So in this case of STRANGeness -1, we have two possible solutions. It's non-perturbative coupled channel approach, so we have chiral unitarity SU3 models, or phenomenological potential models with K-bar N and nucleon-nucleon interactions. And both of these models quite well describe the scattering data above the threshold, as we can see here, and it was already mentioned by the previous speakers. But going to the threshold, we have a lack of data, and below the threshold, since this fact, we have large differences in this extrapolation. And we can see that we have significantly weaker attraction in case of chiral SU3 models than in case of phenomenological potential models. And what we succeeded to do with Amadeus, we determined the cross-section for the K- proton going to sigma 0 pi 0 as well as to lambda pi 0 below 100 MeV, which I'm going to show you today, which is a very important input and to constrain the theoretical models, as well as we succeeded to obtain K- nucleon neutron non-resonant amplitude below the threshold. This is the topic of Christian for tomorrow. I just want to mention about it in this talk. A fundamental key role in the K-bar N interaction is played by lambda 1405 resonance. And we know that this resonance does not fit with the simple three-quark model. And this is commonly considered to be at least partially a K-bar N bound state. And depend on the model which we take into consideration. Okay, we have basically two scenarios. So according to chiral models, this lambda 1405 is a state given by the superposition of two poles in the scattering amplitude. We have a higher mass pole, which is mainly coupled to the K-bar N channel, and a lower mass pole mainly coupled to sigma pi channel. And according to phenomenological potential models, this resonance is a pure K-bar N bound state. Okay, we already heard a lot about the lambda 1405 in previous talks. Okay, the position, basically the position of this resonance reflects on the strength of K-bar N interaction, and it's influencing possible formation of such objects which are called chaonic bound state. And those states were predicted by Akaishi and Yamazaki in the K-bar N interaction in the isospin 0 channel due to the strong interaction. Here we can see the pictures. So this possible chaonic, we also call them a chaonic cluster. The simplest one is K minus with 2 protons, and the decay mode is like lambda proton and etc. And this discovery of such let's call them exotic objects is very interesting, not only on its own, but it could give us information about how strong is the binding of K minus in the nuclear matter, and it has a strong consequences. For example, in astronomy, because it could give essential impact to the equation of state of the neutron stars, because the densities of such neutron stars are expected to be large enough to activate the STRANGENess production. And here we can see what is the predicted density of such bound states or chaonic clusters. It's few times, in case of K minus pp, it's 3 times larger than the nuclear density. Okay, here I summarize the theoretically calculated binding energies and widths of such bound states. So we have chiral models and phenomenological models here, and also experimental results. So the experiments which claim the observation of such, in this case, K minus pp nuclear clusters. We can show it more clear in this scatter plot, where we have this phenomenological, more deeply bound states, more loosely are coming from the chiral calculations, and the experimental results quite spread. So we can see that it's quite puzzling scenario. As we already listened in the second talk, we have a first clear evidence of K minus in K minus induced reaction of such K minus pp nuclear cluster. Okay, anyway, we need some more experimental constraints which allow us to understand better this K-bar N interaction, and of course in the same way the lambda 1405 and related to it chaonic bound states. Okay, and now I'm going to describe this Amadeus experiment, which we performed at Daphne in Laboratori Nazionali di Frascati. Daphne accelerator. This is E+ E- collider. And this collider provides us the charge Kaon beam. We have a back-to-back K+, K- production, and these kaons are produced in phi decay. Phi meson is generated during the electron-positron collisions almost at rest. And this beam is characterized with low momentum, about 120 MeV over C, and a small energy spread, which makes it ideal for this kind of experiments which we performed. Okay, and in this experiment, we use a CHLOE detector, which is cylindrical drift chamber surrounded by calorimeter. As an active target. So we use these CHLOE materials basically in the drift chamber, so the drift chamber gas and the entrance wall. So the carbon, helium, and hydrogen. To investigate the processes of single and multi-nucleon absorption. This detector is characterized with very high acceptance and high efficiency and resolution. So it's perfect for our measurement. We measured K- absorption at rest and in flight. At rest, this is a situation when K- is absorbed from the atomic orbitals, and it has momentum around 0 MeV. And in flight, which is going through the electron cloud and directly interacts with nucleus, and has an average momentum of 100 MeV over C. Okay, and this is the summary of what I'm going to speak. So what we basically do with Amadeus. So our goal is to investigate the nature of lambda 1405 through the studies of K- neutron non-resonant amplitude below the threshold, and this I will show. I will show also this result of the cross-section below 100 MeV, momentum of Kaon, which I mentioned at the beginning. And for these studies, we performed hyperon-pion correlation studies, investigation. Then I will also speak, I will start from this topic. I will speak about the multi-nucleon absorptions and also the investigation of the contribution of the eventual chaonic nuclear clusters. And here we have hyperon-nucleon correlation studies, which I'm going to show you. Okay, as I told at the beginning, I will start from K-. Sorry, I don't know if you see all the presentation. I don't see.
Yeah.
Okay, I don't see the top. So I start from K- nucleon interaction. Excuse me, can you mute someone? I'm hearing you. I'm hearing myself. Okay. Okay, so I continue. So I start from K- multi-nucleon absorptions, which are fundamental for construction of the K- nuclear optical potential. Because how it was shown by Prague Jerusalem group, it's not, it is necessary to include the optical potential, not only single nucleon term, but also multi-nucleon term. And in this way, we are able to feed the kaonic atoms data in the range of periodic table. Okay, so this was done. This was fitted, and okay, maybe I put in, okay, sorry. This was fitted, and then what was done? It was extracted the branching ratio for the one nucleon absorption processes, and it was shown. Here we have the experimental data and some models. It was shown that only some of models like Prague, Kyoto, Munich are in agreement with the experimental data. So in these models, what is taken as this multinucleon term, it is phenomenological global multinucleon term. We want to somehow do more detailed analysis. So this is the step for future, which will allow to include the information about this nucleon absorption separately for 2 nucleon, 3 and 4 nucleon absorption. And this was done with Amadeus. Here we studied K- carbon interaction, and we reconstructed lambda proton final states. These are the kinematical spectra which were fitted by us with all the possible contributions of 2, 3 and 4 nucleon absorption processes. As we can see, we can very well reproduce the experimental spectra with these multinucleon absorption processes. And this is the simultaneous fit for, of course, for these kinematical distributions. And from our analysis, we extracted the branching ratios and the cross sections for these processes which are put in this table. Here we have the global value, which is in agreement with the bubble chamber data. What we also noticed, if we look at the branching ratio of the quasi-free 2 nucleon absorption processes, we can see that the sigma 0 proton is dominant over lambda proton, which is contrary to the ratio which is obtained from the phase space. Yes, from the phase space, and it is recently done the analysis by Stankova and Ramos. And it's interpreted, is our experimental data by the Pauli blocking effect. Okay. In our analysis, we also take into account the eventual formation of the K-pp bound state. As I showed before, our spectrum is very well described only by nucleon absorption processes. And it's due to the fact that when we perform the simulation of the 2 nucleon absorption and bound states, we can see that, for example, invariant mass of lambda proton, that this 2 nucleon absorption is completely overlapping the bound state contribution, except of very, very small with bound state, which are anyway out of theoretical predictions. We repeated the analysis in order to compare it with FINUDA data. FINUDA claimed the observation of K-pp bound state. So we took, they took the back-to-back events, performing a cut in cosine theta. And again, we fit, but here including also contribution from the bound state, and we obtain the same, let's say, the same values like in previous case. So K minus bound state contribution here is completely overlaps with with the 2-nucleon absorption. Our spectrum can be only described by the nucleon absorption, nucleon absorption processes. So we cannot conclude whether this bound state is in our data or not. Another multinucleon absorption analysis is devoted to the studies of lambda triton final state. This is a golden, let's say, in helium-3, it's a golden channel to study for nucleon absorptions. And basically, looking at the previous data taken, we have very small statistics, like from bubble chamber experiment or FINUDA, which provides us only a global branching ratios without the information about for nucleon absorptions. What we did with Amadeus, we determined these contributions, investigating this, as I told, K minus helium-4 into lambda triton. And here we have again the procedure of the fitting data with contributing processes. Here we have very pure lambda triton sample. We measured the triton mass by time of flight. And what we obtained are, for the first, the branching ratios for nucleon absorption processes in this lambda triton channel, as well as the cross sections. Okay, this is the similar analysis, but in carbon 12. Okay. Now I'm going to jump to the single nucleon absorption processes, and I will just introduce you into this topic, which will be described in details by Christian tomorrow. So by Amadeus, we succeeded to obtain for the first time non-resonant transition amplitude below the threshold, so K minus n going to lambda pi minus. This reaction we studied in helium-4. As we can see, here we have theoretically calculated amplitudes below the threshold, and is very big disagreement. So some data are really needed to constrain. Okay, but as I told you, Christian will tell more about it. But what we would like to learn from this, and let's say for what it will be useful for us to extract this non-resonant part in such process. As we know, we have, let's say, two main contributions in such spectrum. Is non-resonant, which is like, let's say, direct, and resonant, it's from sigma 1385 in this case. So here, this process is quite well known, so we were able to extract this non-resonant amplitude. And extracting this non-resonant amplitude, we would like to comment somehow on this non-resonant bias, which is in case of lambda 1405. If you want to disentangle resonant and non-resonant part. So in order to well study the lambda 1405, you want to, how to say, remove this non-resonant fraction from our sigma 0 pi 0 spectrum. This is our measurement. So this is one of the biases. Second bias is related to the kinematic threshold of the absorbing nucleon binding energy. However, we can somehow, which is limiting the higher pool. Okay, but this we can somehow reach by the in-flight process. Okay, it opens us the window for this studies, but more will be said by Christian Pischikia. So by this we want to somehow study the lambda 1405 properties. Okay, and now I'm going to the last result, the most recent result, which is the cross-section determination below the 100 MeV for K minus proton going to sigma 0 pi 0 and lambda pi 0. What is the motivation of these studies? So till now we have only 3 points measured in experiments. These are bubble chamber experiments, and these points have very large uncertainties, larger than 30%. What's more, K minus proton to sigma 0 pi 0 is not obtained directly, but on the basis of isospin symmetry argument from the second process. Okay, sorry. And here we have some theoretical calculations. So this region is really poor, and in order to constrain it, it is a very needed experimental point, which will be a fundamental input as for the calculations. How we extract this cross section? So we analyzed K minus hydrogen process going to sigma 0 pi 0. And again, we fitted the obtained kinematical spectra simultaneously with the contributing processes. For us, interesting processes in flight. So these red lines here, we have invariant momenta, total momenta, invariant mass, cosine theta. In case of lambda pi 0, it is similar procedure. Instead of cosine theta, here we used momenta of lambda and pi 0. And from this analysis, I'm not going to talk about the details because it's preliminary. We obtain these 2 points, so corresponding to the cross section of K minus P to sigma 0 pi 0 and to lambda pi 0. And they are determined with much lower uncertainties. We also put uncertainty on the momentum. So let's say this is one of the most important results now, and I think it's first time shown in public. So we are preparing now a paper, and it's going to be published soon. Okay, and let me now summarize my talk. So I show you the status of our studies which we performed, which were performed by Amadeus collaboration, namely single and multinucleon absorption studies. So I showed the main results regarding the branching ratios, cross sections obtained for the first time for multinucleon absorption processes, and I introduce a bit about K minus n amplitude below the threshold, which is very important, also to put constraints for the theoretical calculations. And I think the most recent and quite important is our latest result of the cross-section below 100 MeV for K minus proton to sigma 0 pi 0 and lambda pi 0. And thank you very much for your attention.
Okay, thank you very much, Magda, for showing these new results. And we are a little bit diverging from the schedule, so I would suggest to use the chat for any comments, or we can move it to the discussion session, because Jarka is going to talk about the multi-ionic absorption in the next contribution. So I would just directly move on, if you don't mind.
Okay.
So yeah, there are some raised hands, but let's use the chat, because we are 10 minutes off and it can become late for the Japanese colleagues. Okay, thank you once more. So Jarka, are you there?
Yes, do you hear me?
Yeah, well.
So I will start to share my screen. Oh. Do you see my screen?
Yeah, it's fine.
Okay, full screen now.
Yeah, perfect. Yeah. Okay, so you have 20 plus 5 minutes.
Okay. So thank you. So as Daniel already said, I will speak about our microscopic model of K-2 nucleon absorption and its application in conic calculations.
Ah, perdón, sí, gracias, acabo de llegar ya. Perdón.
Sorry?
Eulogio, can you please mute?
Okay, so this work was done in collaboration with Ángeles Ramos, Eli Friedman, and also Jiří Mareš. So the absorption of K- on 2 or more nucleons represents about 20% of all K- absorption in the surface region of atomic nuclei. And so far, it was described mainly by phenomenological optical potential fitted to reproduce the multinucleon absorption fractions. But Sekihara et al. Connected this 2-nucleon antichaon absorption to modern chiral meson-baryon interaction models and developed a first microscopic model for K-NN absorption in nuclear matter. And in the model, they used only free space chiral amplitudes to evaluate the K-NN absorptive potential in nuclear matter. And as we heard recently, Amadeus collaboration provided new experimental data on the K- multinucleon absorption. So there is really need to have a really solid theoretical model for K- 2 nucleon absorption, which would be connected to modern chiral K-N interaction models, and of course capable of reproducing available experimental data. So a very important source of information about K- nuclear interaction below threshold are kaonic atoms. And their analysis give us unique information about the K- nuclear potential. And a sensitive test of any K-baryon interaction model near threshold is its ability to fit the broad database of kaonic atoms. However, when you do that, when you construct the potentials based on single nucleon chiral amplitudes, these potentials are generally unable to fit the kaonic atom data, as you can see here in this table, where is the value of chi-square per 65 data points for various state-of-the-art chiral models. And the reason is that the considered chiral models do not address the K- interactions with 2 and more nucleons, which are of course important for the realistic description of K- nucleus interaction. And in analysis of kaonic atom data by Friedman and Gall, the phenomenological potential describing K- multinucleon processes was added to the optical potential constructed from the state-of-the-art chiral K- amplitudes. And this potential is of this form, where complex amplitude B was fitted to the data for each of the chirals models separately. And adding such a phenomenological density-dependent multinucleon potential yields much better agreement with canonic atom data and equally good fit for all considered chiral models. Then value of chi-square for 65 data points goes down to 100 up to 125, which is much, much better. Next, one can distinguish between different K-bar-N models by testing their ability to explain experimentally deduced values of single nucleon absorption fractions from bubble chamber experiments. And analysis of canonic atom data revealed that only 3 of the considered models, namely Prague, Kyoto, Munich, and Barcelona models supplemented by this multinucleon phenomenological potential, are able to reproduce simultaneously canonic atom data and K- single nucleon absorption fractions. And the compatibility of these 3 models was with the data was also confirmed in a recent measurement of K-N to pi lambda amplitude by Amadeus collaboration. And recently we have developed a microscopic model for K-2 nucleon absorption in symmetric nuclear matter. And the description of the K-2 nucleon absorption in our model is based on the meson exchange picture. In the model, we employ a scattering amplitudes derived from Prague and Barcelona K-bar-N models, and we take into account the medium modifications of the free space amplitudes, and we derived also the real part of the K-NN potential. Moreover, we derived the K- single nucleon potential within the same approach, and this way we could obtain single nucleon, two nucleon, and total K- optical potentials within the same approach and the same chiral model. So the K- absorption on a single nucleon can be described or represented by this Feynman diagram. Here, these shaded circles denote the K- and T matrices derived from a chiral model. The K- 2 nucleon absorption is described as a meson exchange process, and here are depicted Feynman diagrams representing the absorption of K- at rest on 2 nucleons, N1 and N2 in nuclear matter. And these dashed lines between the loops denote the virtual meson exchange, such as kaons, pions, or etas. And we also considered contributions to the K-NN self-energy from these exchange diagrams, which are depicted here. And these diagrams result from antisymmetrizing the initial N1 and 2 state, as well as from exchanging the place of nucleon and hyperon in the final state. So we build the total K-N and K-NN optical potentials as a sum of potentials coming from possible absorption channels. For the K- single nucleon absorption, we consider, or we have 7 possible channels with pions, lambdas, and sigma in the final state. In the case of 2 nucleon absorption, we also have 7 possible channels with lambdas, sigmas, and nucleons in the final state. However, each of these channels can be described by several direct and exchange diagrams, depending on the possible meson exchange. So the total K-NN potential is a sum of potentials coming from direct and exchange diagrams in each channel. And now we go to some comparison with experimental data. So as we heard in the talk before, the Amadeus collaboration recently measured the K- multinucleon absorption in reactions of low energy K- with carbon, and they measured the ratio of branching ratios for quasi-free production of lambda proton and sigma 0 proton pairs. So we calculated this ratio within our model using Barcelona and Prague models amplitudes. You can see those ratios as a function of relative density plotted in these 2 figures. And the Amadeus experimental value, including the error bar, is denoted by this gray box. And here in black, the black lines denotes the ratio evaluated using only free space amplitudes. So as you can see, in both cases, the ratio lies above 1 and out of the gray box within the relevant density region. But when the Pauli blocking effect is taken into account in the amplitudes, the ratio lies within the error bar of the experimental value in the relevant density region. And this result nicely illustrates the importance of medium modifications of free space amplitudes. Next, we calculated within our model the K- single nucleon absorption fractions. And we calculated them first using the free space amplitudes and then also with Pauli blocked amplitudes, Barcelona amplitudes at the 30% of saturation density. Why this density? Because we consider this density region as relevant for absorption of low energy K- on carbon-12. And we compared our ratios with the bubble chamber data, which are corrected for secondary interaction of the primary particles created in absorbing nucleus. That means they are directly comparable with our ratios. And as you can see, the mesonic branching ratios calculated using Pauli blocked amplitudes are in much better agreement with experimental data, especially in the case of sigma plus pi minus and sigma minus pi plus final states. The total one-nucleon ratio is also consistent with experimental data. Next, we calculated also branching ratios for K- 2 nucleon absorption into different final states. Again, we did the calculations with Barcelona Pauli blocked amplitudes at 30% of saturation density. And we compared these fractions with directly measured values, which means uncorrected for the effect of secondary interactions. And for a proper comparison, now we had to consider some final state interaction effects, mainly sigma n, lambda n conversion. So in a column A, we considered 60% probability for sigma plus to lambda conversion, 22.5% probability for sigma minus to lambda conversion, and 72% for sigma 0 to lambda conversion. And in column B, we take 50% conversion probability for all sigmas. And we can see that the corrected two nucleon absorption ratios agree much better with the experimental data. And in the lower half of the table, we present the branching ratios for the total sigma plus, sigma minus sigma 0 and lambda production stemming from both K- single and two nucleon absorption. And the branching ratios, including sigma lambda conversion, again show very nice agreement with the data. And moreover, the total sigma plus, sigma minus ratios tends to favor option B for sigma lambda conversion rate. So the above microscopic K- NN model was recently applied in kaonic atoms calculation in order to test its validity also here. And we calculated energy shifts and widths for selected atoms. And in the calculations, we employed Barcelona, K- and amplitudes. And of course, we took into account the in-medium modifications of the amplitudes due to Pauli principle. And we used the subthreshold kinematics for the amplitudes derived from our K- NN model, and also from the form from previous analysis of kaonic atoms by Friedman and Gall. And in this table, we present values of chi-square calculated for shifts, widths in selected atoms, and calculated using only chiral K- and potentials. then K minus N plus microscopic K minus NN potentials, and K minus N plus phenomenological multinucleon potentials. And these calculations were performed using free space Barcelona amplitudes modified by WRW procedure, which is just a different approach to account for Pauli correlations in the medium, and then with the Pauli blocked Barcelona amplitudes. And the experimental data are shown here for completeness. So our results shows that the description of the data is indeed improved when the two-nucleon absorption is included, and that the calculations with the Pauli amplitudes yield a better description of the data than calculations with WRW modified amplitudes. And of course, the microscopic Kn plus Kn potentials cannot compete with the phenomenological one, which includes also processes on 3 and more nucleons. And as a next step, we calculated the microscopic K minus N plus K minus NN potentials for 23 nuclear targets and provided them to Ellie, who confronted them with the conic atom data. And the microscopic potentials were then also supplemented by a phenomenological term describing the processes on 3 and 4 nucleons. And the parameters of this term or of these phenomenological potentials were fitted to the data. And so far we analyzed 2 sets of potentials. First one based on Pauli blocked amplitudes and subthreshold kinematics from the K-NN model. And the second set of potentials with WRW modified amplitude and subthreshold kinematics from conic atom analysis. And here are results of the fit for the first set of potentials calculated with the Pauli blocked amplitudes. We obtained, or the fit resulted in 2 branches. The first one with the real part of the additional phenomenological amplitude larger than 0, which means attractive, a real additional phenomenological potential. And this plot shows the values of chi-square and real and imaginary part of the amplitude B as a function of parameter alpha. And you can see there is a well-defined minimum for alpha around 0. But note that the imaginary part of the amplitude in this case is negative, which unfortunately means negative absorption for the additional phenomenological term. And this result suggests that we would need the microscopic potential with more attractive real part and less absorptive imaginary part. The second branch of the fit yielded negative real amplitude B, which means repulsion. However, the imaginary part of the amplitude is negative also in this case. And here in this slide, there is a summary of resulting parameters for both branches of the fit, in this case with Pauli blocked amplitudes. In the both solutions, unfortunately, have negative value of imaginary amplitude, which means that the original K-N plus K-N potential is just too absorptive. And in other words, like there is no space for the additional absorption on 3 or 4 nucleons. And this table shows the evolution of chi-square for K- potentials based on Pauli blocked Barcelona amplitudes. The pure K-N potential would yield value of order of 700. Then adding the microscopic K-NN potential significantly improves the fit down to about 300. And then adding the phenomenological 3 and 4 nucleon term further decreases chi-square to about 133. For comparison, there is also the best fit chi-square for the K-N plus phenomenological multinucleon term. In addition, we tried to feed the data with a rescaled total K minus n plus K minus nn potential, and the feed yielded scaling factor of 1.68 for the real part and 0.57 for the imaginary potential, with chi-square per 65 data points of 130. And this result is an agreement with the first branch of the fit, and tells us that in order to fit the data, we would need a microscopic potential with more attractive real part and less absorptive imaginary part. Then the second option with W or W modified amplitudes resulted only in one solution, in this case with the positive amplitude B, which means through absorption. And here there is a result for the parameters of the additional phenomenological potential. The real part of the amplitude is negative in this case, which means repulsive additional phenomenological potential, but the imaginary amplitude represents a true absorption. In this table, there is again the evolution of chi-square for K minus potentials based on Barcelona amplitudes modified by WRW procedure. The pure single nucleon potential yields value of order of 2000, almost 3000. Then again, adding the multi-nucleon, the microscopic K minus n potential significantly improves the fit down to about 1100. And adding this extra or additional phenomenological 3 and 4 nucleon term further decreases chi-square to down to about 116. And in this case, we also did this additional fit with a rescaled total K minus n plus K minus n microscopic potential. And the fit yielded a scaling factor for the real part equal to 0.32, and scaling factor for imaginary part equal to 1.19, which means that in this case, we would need, in order to fit the data, we would need potential with less attractive real part and slightly more absorptive imaginary part. Okay, this brings to my conclusions. So we have developed a microscopic model which describes the K minus 2 nucleon absorption in nuclear matter using scattering amplitudes derived from Prague and Barcelona chiral meson baryon interaction models. And in the model, we confirmed the important effect of medium modifications of the amplitudes. And our calculated ratios within the model are in a good agreement with experimental data. And then we applied this microscopic K minus nn model in the calculations of kaonic atoms. And the preliminary results show that the description of kaonic atoms indeed improves considerably when the microscopic K minus nn potentials are included. Also, that the data are better described by K minus n plus K minus nn potentials based on Pauli blocked Barcelona amplitudes. But we still need to supplement the microscopic K minus n and K minus n potentials by some phenomenological term to account for K minus 3 nucleon and or 4 nucleon processes, and of course to further decrease the value of chi-square. So the analysis is still in progress, and we are working to get new results, which means we need to still test different options for subthreshold kinematics, then include in medium modifications, which would include also hadron self-energies, as well as we would like to test also other K minus and interaction model, namely the Prague one. So that would be all from me. Thank you for your attention.
Okay, thank you, Erka. Thanks for showing these new results, new calculations. So there is a time for questions. Yeah, I see Lokio was the first one. So Lokio, please go ahead.
Nice work. I mean, very nice work. Congratulations. So let me ask you a question. I mean, prior to this detailed calculation, I mean, there was already available absorption, because Angel Ramos and we calculated also, I mean, there are kaons in the medium simply by using the chiral unitary approach and dressing the kaon propagator with the self energy which we had calculated, and then we did that, I mean, iteratively, I mean, to reach self-consistency. So, okay, then it is true that by doing that, I mean, you generate many of the diagrams that you have automatically, but it's also true, I mean, that some of the diagrams that you have, one doesn't generate. All these cross diagrams, I mean, I know you don't generate. So, but now the question is that, I mean, when this potential that we obtained was used also for chaotic atoms, the results were decent. Well, perfect, but were quite good. It was work done by Okumura and Hirenzaki and Angels. So then I don't know where you have compared. I mean, how much different is the one that you obtained compared to the one that was obtained by your collaborator, Angel Ramos?
Well, we did not compare these potentials with these previous calculations. Not yet. We can do that, but we didn't do that with Angels.
I just want to say something.
Yes. Thank you for the question. Actually, Yarka is asking me to produce the amplitudes modified because we wanted to work with the new Barcelona model, the one that was developed by Albert.
Yes.
And we need to implement not only Pauli block, that this is what we did with Yarka 1 or 2 years ago, but we need to implement also all these self energies. And we have not done it yet, self-consistently. And we are in the process of doing that. But we have not. We could have also used the old amplitudes, but we have not done that yet either. So, so we need that is something that we need to implement.
Fine. Okay? Let me go back, I mean, to the girl, I mean, and ask her. I mean, you say there at the end in the conclusions, the description of chaotic atoms improves considerably when microscopic KNN potentials are included. What does it mean? You mean when you take only real part and then you put? No, I mean.
No, we did the full microscopic calculations when where we constructed the optical K-N and K-NN potentials from chiral amplitudes and including real and imaginary part, and we calculated energy shifts and widths of chaotic atoms.
Yes.
And we calculated also chi-square for these results compared to the experimental data, and we saw, like I showed in this table,
yes.
This is just for a few atoms that the chi-square you can see here drops. And also the fit to the data by Ellie. We provided to Ellie potentials, microscopic potentials calculated for all for 23 nuclear targets. That means to cover all the experimental data he is fitting to. And again, the fit confirmed, like for example here, that when you add the full microscopic K-NN potential, then you decrease the chi-square. You describe the data better.
Understand. Okay, good. Thank you very much.
Okay, there is a question for Laura. Maybe a quick one, please.
Okay, I was wondering whether, meanwhile, you can also calculate the absorptions rate of K minus and maybe even the rates of K minus to K plus disappearance in experiments like pion-induced experiments, and not only with kaon-induced experiments, comparing small nuclei and large nuclei, since we have data for that.
And I didn't get the question.
Whether you can calculate the, let's say, sort of absorption rate for K minus No, in pion-induced reaction, where pion are beams, and then kaons and anti-kaons are produced inside the nucleus, and then they might get absorbed.
So the ratio of K minus K plus production?
Yes, well, not only production, but also, let's say, absorption, because in the experiment, obviously, you cannot distinguish between production and absorption because you measure only the final state, right? And I mean, I can put the paper I'm talking about, the measurement, in the chat. Maybe you can have a look. But it seems to me that now with your calculation, you could also try to, let's say, evaluate the K minus absorption in carbon and lead nuclei and see whether your calculation reproduce also this data. Well, maybe you can have a look and see whether this can be done.
Okay, you can send me the link for the paper, but yeah, I can.
The chat. I put it in the chat.
Okay, we can have a look on it.
Okay, yeah. Okay, so thank you once more, Jarka. And Angels, did you still wanted to add something? You're raising the hand.
No, I forgot to lower the hand.
Okay. So let's move on to the few body sectors with anti-kaons. And so the next speaker is Nina Shevchenko.
Can you hear me?
Yeah, I can see you. So I can share the screen. Yeah.
Okay.
Yeah, it's not in full screen, but I can hear you very badly.
Is it better now?
Yeah, much better.
Much better.
Yeah.
Do you see my slides?
Yeah, I see the slides, but they are not full screen. So.
I see it as full screen, so I don't know. What can I do?
Well, I think it's fine. It's visible.
Okay. Fine, then I'll start. Hello, everybody. I'd like to tell about the quasi-bound state, which I found out in the Newton proton system. And it's not conic deuterium, which is known, but it is some state which is caused by strong interactions. The whole history started from predictions of the proton-proton system, quasi-bound state in it, made by Akaishi and Tamazaki. And after that, many experimental and theoretical efforts were spent with different results. We also made a set of calculations. We performed a series of dynamically exact calculations of 3-body anti-kaon nucleon systems. In particular, we evaluated the binding energy and width of quasi-bound states in K-bar and N system, which spin 0, and K-bar, K-bar, N systems. And we found nothing in another spin state of the K-bar N system, which is usually denoted as K minus neutron proton. Here I recognized when I was listening to Professor Iwasaki that it would be probably nice to say that when we are speaking about K minus proton-proton quasi-bound state, we mean also the quasi-bound state in the K-bar 0 Newton proton system, because from the point of view of strong interactions, these systems are absolutely equal. The same is true for the spin 1 K-bar system, which can be denoted as or understood as K minus Newton proton or K-bar 0 neutron system. We also calculated near threshold scattering in the K-bar N system with spin 1, which is K minus neutron system in principle. And all this was done using Faddeev type AGS equations with coupled K-bar N and pi sigma n channels. And we also studied the conic deuterium, which is an atom, which is mainly caused by Coulomb interaction. The most accurate our calculations was done using Faddeev type once more equations, where we directly included not only strong interactions, but also Coulomb interaction. Here, I show that we found nothing in this spin 1 state of the K-bar N. And it was proven that there is nothing in it. So first of all, I want to underline that it is namely the quasi-bound state, which is caused only by strong interactions. It's not the conic deuterium. There was some evidence that something can exist in this system because we calculated, among other things, K-deuterium scattering length. And when we performed analytical continuation of the effective range formula for this scattering length, which we calculated below the K-deuterium threshold, we found out that some quasi-bound state really can exist with this not very much, but quite sufficient binding energy about 14 or 20 MeV, and with 15 or 22 MeV. But when after that we performed systematical search for the states using our three-body Faddeev type equations, we found nothing. We found no corresponding poles in the complex energy plane. The reason of this discrepancy between this evidence and the fact that we found nothing is that the effective range formula which we used and which many other people use for estimation of such things is valid only in the vicinity of the corresponding threshold. But for this quasi-bound state in this K-Newton proton system, large binding energy and width were expected. That's why this formula is out of the validity region. And I said we not only found nothing in the complex energy plane, but we also proven that there is nothing. We did it in this way. We changed the K anti-K nuclear interaction by hands. So we just times our strength constant of our interaction by some constant, changed it from some 1.25 to 1 gradually, and performed a series of calculations which are denoted here by dots. And when this constant is large enough, which means that anti-K nuclear interaction is larger, much larger than it is, we found some quasi-bound states in this system. But when we, sorry, it's here. But we gradually we're performing our calculations with decreasing this constant. We moved to actual values, which are not quasi-bound states anymore. So in our three-body calculations, we found out that there is nothing in this system. However, after performing our three-body calculations, we moved to four-body calculations of the K-bar NNN system. Once more, we used Faddeev type equations, which is much more complicated, hard, and so on. And for these calculations, we constructed new nucleon potential. Before we used some potential which was provided by us by Paul Dolishal, but we decided to construct our own. And when I started calculations or some numerical tests of my four-body numerical code, I found out that the quasi-bound state in this K- Newton proton subsystem caused by strong interactions appeared. So here is my new nuclear potential, which I constructed for the four-body calculations. It is two-term separable potential. It looks like this with Yamaguchi, or some of Yamaguchi form factors, gamma, beta, and lambda are some constants, which were fitted to argon 18 potential first shifts. This potential, this nuclear potential, reproduces perfectly, very well. Neutron, proton, and proton-proton scattering length, effective range. Of course, the potential gives proper deuteron binding energy. And here you can see the first shifts. Those provided by argon 18 potential are denoted by circles for neutron-proton and for proton-proton nuclear potentials. And you see that our lines reproduce the first phase shifts very well. And if we are talking about K-bar system, of course, the main interaction is the anti-count nuclear interaction. We used 3 hour potentials, which were constructed before. 2 of them are phenological potentials. One of them has 1 pole, lambda 1405 resonance. Another one is the 2 pole, has 2 pole structure. And the third potential is our once more chiral motivated potential. It couples all open channels, K-bar n, pi sigma, and pi lambda. And as the most of the chiral potentials does, it has 2 pole structure of lambda 1405 resonance. And all these 3 potentials with the same level of accuracy reproduce 1s level shift on width of County hydrogen, of course, measured by Siddhartha collaboration. It was done by direct inclusion of clone interaction into Lippmann-Schwinger equations. We don't use some desert type formula for this. Our potentials reproduce elastic and inelastic K-means proton cross sections and threshold branching ratios, gamma, and these 2. And of course, all our anti-count nuclear potentials somehow reproduce or includes lambda 1405 resonance, which according to particle data group has these parameters. Here you see experimental regions for 1s level shift and width of County hydrogen. And to see that 3 hour points are inside Siddhartha region, which is good. Here are the cross sections, elastic and inelastic. And here the lines are our 3 potentials, results of our 3 anti-count nuclear potentials. You see that they reproduce experimental data very well. And here I show the poles, strong poles, which are given by our anti-count nuclear potentials. You see here we have only 1 pole, and for the 2 other potentials, there are 2 poles which form lambda 1405 resonant, and it really demonstrates itself in, for example, pi 0, sigma 0 elastic cross sections. Here I plotted it for chiral potential only, but you see that in spite of the 2 poles, there is only 1 bump in the proper region. I said that I found out this quasi-bound state when I was performing, in fact, 4-body calculations, but to study this state in more details, I solved the 3-body Faddeev type alt AGS equations separately. So these are the equations. They couple particle channels where there is K-bar n and pi n sigma n. Input for our equations are 2-body T matrices corresponding to 2-body potentials. First of all, to the potential of anti-count nuclear interaction. As I said, we use 3 versions of it. It is also nuclear potential. Since we have this additional channel we need to include somehow sigma nucleon potential, which is coupled to lambda nucleon potential. It is also some our potential which we constructed sometimes before and used for our three-body calculations. And parameters of this potential were also fitted to experimental cross sections. So the quantum numbers of the system which we want to investigate are, first of all, spin 1. The total orbital momentum of the system is equal to 0 since all our two-body interactions are in S waves. Isospin of the system is equal to 1/2. And if we are once more speaking about the system in isospin representation, it is K-Baronian system with JP is equal to 1 minus. And if we are speaking about particle representation, it is either K minus neutron proton or K bar 0 neutron system, the system which Professor Iwasaki was talking this morning. And here you can see the results of our calculations. Here there are binding energies and width of the quasi-bound state, which were found in the K minus neutron proton system. Energy here, binding energy, is calculated from the threshold of K minus neutron system. So it's calculated from, it is moved by 2.2 MeV down in comparison to K minus proton system. And here you can see the result of two different calculations, the coupled channels calculations and the calculations one channel with exact optical K-Baron potential. The coupled channel calculation is, how to say, it's much more exact. It's, well, much more accurate. It's in fact exact. It is something which we can do when we are solving only three-body calculations. But when four-body calculations are done, it is very complicated itself, even without additional particle channels. So something which will be included in four-body calculations, it will be this exact optical version of this calculation, in fact. So if we are speaking about coupled channel results, we found out that the phenomenological potential with one pole lambda 1405 resonance gives nothing. It is the same situation as with the previously used nuclear potential, but both potentials, anti-nuclear potentials with two poles of the lambda 1405 resonance give some quasi-bound state in the K minus proton-neutron system. You see that binding energy is very small, it's about 1 MeV, but the width is not small, it's in fact comparable with the width of the K minus proton-proton quasi-bound state. When we performed these one-channel calculations with exact optical K-Baron potential, the quasi-bound state appeared also in this with this anti-count nuclear potential, and the numbers for the other two slightly changed, but not drastically. So we found out that really in this K minus proton neutron system can exist a quasi-bound state equal to those as in the K minus proton system. If we are speaking about K minus proton system, of course, if we have new potential, we can try what will change if we perform calculations of this one. And here are the results for the K minus proton system. Here once more, I show the results of the coupled channel calculations with new nuclear potential. The one channel calculations with exact optical K-Baron potential with new nuclear potential. And here for comparison, there are our previous results, which were calculated with coupled channel results, coupled channel calculations. So first of all, we see that once more here, couple channel and one channel with exact optical potential results are very close for binding energies. You see here, they're very close, especially for binding energies. They're slightly more different for the width. You see here 4 MeV difference, here as well, here almost the same. And if we compare our new results with new nuclear potential with those obtained with the previously used nuclear potential, we see once more that the results are very, very close each to other, which means that nuclear interaction plays a minor role in this K-bar system. In fact, it is the same for this system, for the K-mass proton-neutral system, but since this quasi-bound state or pole corresponding to the quasi-bound state lies so close to the threshold of this system, the particular choice of the nuclear potential can resolve the question whether this quasi-bound state exists in K-mass neutron proton system or not. So I can summarize and say that quasi-bound K-mass neutron proton state caused by strong interactions only was predicted. Its binding energy is small, it's about 1 or 2 MeV, while the width 40 up to 60 MeV, depending on the anti-Nucleon potential used, is comparable with the width of the K-mass proton-proton quasi-bound state. I've shown that the particular model of the nuclear potential plays a minor role in the K-mass proton-proton system, and the same is true for the K-mass neutron-proton system. But since the quasi-bound state they is situated so close to the threshold, the potential, nuclear potential, can resolve the question of the K-mass neutron-proton quasi-bound state existence. And finally, I remind that it is a quasi-bound state which is caused only by strong interactions. It is strongly bound, and it is much broader than conic deuterium, which also exists in this system. Therefore, the atomic and the strong quasi-bound states cannot be misidentified. So that's all. Thank you for your attention.
Okay, thank you very much, Nina. And yeah, we have a time for questions or comments. I see one, I think, from Eulogio was the first one.
Yes,
so go ahead.
Yes, I wanted to ask, let me see, you have the K minus neutron proton. K minus neutron proton will have two isospin components. I mean, isospin 0 and isospin 1. If you take the isospin 1 component, then it is like the K minus proton-proton. So then why is there that you get so different results? I mean, K minus proton-proton, you get binding by 30 to 50 MeV. And here for the neutron proton, even if you have also an isospin 0, 1 component, for the neutron proton, you get such a small binding or no binding at all. Can you give me some reason for that?
Well, we can look at this in very simplified way, that K-mass proton-proton system is doubled K-mass proton system. So it is twice more bound than lambda 1405 resonance, which is a quasi-bound state for the K-mass proton. And if we have K-mass proton-neutron system, we have only once K-mass proton.
Correct, but that's I would guess that the binding could be half, but not such a drastic change from 50 MeV to 0.9 or 0.
No idea. No, it's quite hard to understand why it is something like this in three-body system.
Yeah, I know. But the systems are very subtle, and one cannot make a priori guesses. But anyway, it's curious. The comment is that the result is curious.
Okay, thank you.
Okay, thank you. So the next one was Professor Witczek. So please.
Yeah, you may be surprised, but I will show you tomorrow a kind of experimental evidence that this state exists. It's very odd story, and it takes few minutes to discuss. So I will postpone it till tomorrow. Okay, thank you.
Okay, thank you very much.
Okay, thank you. So we'll be excited for tomorrow. And I don't see any more questions. So let's switch the gears a little bit and move to the baryon field. So the next speaker is Raquel. So. Yep, perfect. Okay.
Okay. So first of all, I would like to thank to the organizers for giving me the chance to present this talk. This is a work that I have done in collaboration with Natsumi Keno and Eulogio Oset. The title is The Two-Step Mechanism Explaining the Dibaryon DStar 2380 peak. So in principle, this has nothing to do with STRANgeness. However, the reaction mechanism that we are going to study can be straightforward, extended to the STRANgeness sector. And what Albert Feijo showed this morning is just an extension to the STRANgeness sector of one of the step mechanisms that we are going to study. So the dibaryon peak appears in the p proton-deuteron collision going to deuteron pi 0, pi 0, where one of the protons inside of the deuteron acts as an spectator. So this data for several energies, kinetic energies of the proton, 1.2 and 1.4, they are shown in colors red, black, and blue. And you can see that there is a nice peak around the position of the claimed dibaryon with a mass of 2.37 GeV and a width around 70 MeV. So there are several calculations of the T-channel delta-delta contribution, which is the dashed line. And if you have an NN star Roper excitation in the intermediate state. And this is the dotted one. And as you can see, these two processes cannot explain the peak of the dibaryon. So the peak has also been seen later in 2013 in PN going to deuteron pi plus pi minus with approximately the double strength. As you can see here, this cross section is multiplied by 2. This reaction has isospin equal to 0 and 1, and the isospin equal to 0 has been singled out. So in principle, we will study this reaction in isospin equal to 0. So the possible quantum numbers which are favored, they have been classified by the experimentalist, and isospin equal to 0 and T plus are the dominant quantum numbers. So a possible interpretation of this peak has been a delta-delta bound state. So the first question to ask is whether this is a new state or there is another possible interpretation. So in fact, if we go back to the 70s, there is a work done by Barnier. At that time, there were very poor experimental data. Still, he concluded that the dominant process of the two-pion reaction was driven by two-step mechanism where you have a neutron proton in the initial state going to pion proton-proton, and then in the second step you have that the proton and the two protons they fuse in order to give the delta and the nucleon. So this reaction has been studied by several authors, and they have concluded that the dominant channel in the intermediate state is the delta. So nowadays, we have much more precise data on the first step mechanism. And this data has been, they have come 2020, and they basically come from a subtraction of two differential cross-section. So the errors are expected to be large since you are subtracting two different cross-section. And as you can see here, the authors in this paper, they have fitted the experimental data points to a resonance with mass of 2,315 and with around 150 MeV, claiming that it would be the Roper resonance. However, there are calculations of this mechanism done in 1998, where the Roper resonance basically it gives this dashed line and cannot reproduce the data in this site. And actually, you can see here that this is too wide, while here you have two data points that say that you should have one narrow structure around there. So for the second step mechanism, we have the fusion of two protons going to pipeized deuteron, and this is indeed very large to be a fusion reaction. So the question to ask is whether the peak that has been seen in the first step and the second peak in the second step, they can interference in order to give in the full mechanism the peak of the divariant. So for the second step mechanism, as Alberto Feijo has shown for K minus deuteron going to proton sigma, so instead we can change here the sigma by a proton and the K minus by the pi plus. So we will see that indeed the second step process, the one of the two proton fusion reaction, is very big, indeed, because there is a triangle singularity which dominates this mechanism. So triangle singularities, they were introduced by Landau in the 60s, and the Coleman-Norton theorem states that the triangle singularity occurs when the three particles in the loop diagram, they can be put on shell, and they are collinear in such a way that the process can occur at the classical level. So we can start from a scalar 3-point loop integral. And then from here, if you do the integral of the Q0 variable, you have the two propagators that dominate the analytical structure of the integral. You have, in fact, two integrals, one in the momentum and another in the cosinus of theta. So this is one of the cuts that gives the cut when the particles 1 and 2 are on shell. While for the other cut, you have that particles 2 or 3 instead are on shell, and that FQ has, in fact, endpoint singularities or logarithmic branch points when the cosinus of theta is equal to plus minus 1. And this basically means that the particle 2 is antiparallel or parallel to the momentum of the 2-3 system in the frame of the decaying particle. So for Z equal to -1, there are in fact two solutions. For Z equal to 1, there is these two solutions. This one has momentum negative and cannot be fulfilled. And here we have these two, QA plus and QI minus. You can see here that this sign basically means that the momentum of particle 2 is in opposite direction in the frame of 2-3 system than in the frame of the decaying particle. So basically in the frame of the 2-3 system, what you see is that the particle 2 is approaching. So it goes sufficiently slow so that particle 3 is faster and it catches particle 2 and fuses into the final state. While in this case, particle 2 is too fast and particle 3 cannot catch it. So the condition of the triangle singularity basically comes when the momenta of the intermediate 1 and 2 particles is equal to the momenta QA minus when 2 and 3 are on shell, and 1 has the singularity basically because this logarithmic branch, they cannot cancel because the cosinus of theta cannot be larger than 1. So then you have a singularity in the integral. So you have here the different situations. So in the situation A, you have here the singularities, and you can build a path so that it does not pinch any of the singularities. While in the case of B, you have QA plus is equal to QA minus. This would mean that P2 star is equal to 0, and then we have just the two-body threshold singularity. While in the third case, this is the case of the triangle singularity. So you can see here several famous examples of triangle singularity, which are getting very popular, and I recommend you to look at this review written by Bo. So we go now to study the second step mechanism. And in here you have the two protons that they fuse in order to, they go back to back, and then they give the delta and the proton. And then as I said earlier, the neutron goes faster than the proton and it catches with the proton to give the deuteron. The condition of the triangle singularity basically is fulfilled when the square root of the energy is 2179 MeV for the width equal to 0. However, the delta particle, it has a width, so what we see is a broad peak. And actually, the deuteron has a binding energy of 2.2 MeV, so these two cannot be on shell. But for continuity, we see still the peak in the amplitude. So these are the two structures that we have to consider, and then we can build PP wave function antisymmetric in this way, and the same for the deuteron. For the isospin-spin wave function, we know it has a spin equal to 1. So we can write down the integral in this way. For the delta down diagram, the same, but then changing the momenta of sign. And then when we perform the integral in Q0, we obtain this momentum dependence. So basically we have the two important cuts here when the two nucleus and the pion, they are on shell, and here when the delta and the nucleon are on shell. So these are the two cuts that they give the triangle singularity. The spin operators, they, if you calculate the elements, you get something like this. And for the initial state, you can have up, up, or up, down. And for the final state, you have these three combinations. And the same if you just flip up, up to down, down, or just the spin of the initial state. So basically, you can cast the dependence in the momentum in this F function and the spin dependence in this Q. And you can see here that these two terms, the delta down and delta up, they have an opposite sign. So for the pion, we have considered the full pion propagator, and we have not done any static approximation. And this is what we get for the differential cross-section. So another question is we need to relate the wave function of the deuteron to the coupling of the deuteron. And for this, we go to this paper. And since the amplitude has a pole around the mass of the deuteron, we can relate this to the scattering length of the deuteron. We take the experimental value, and from there we evaluate the coupling. And this gives us the coupling. And we can compare also with the standard formula Weinberg, and we see that the value that we get is indeed very similar. Actually, we also use the deuteron wave functions, and this comes into the substitution of this propagator, where you have the two nucleon and the pion on shell by the wave function of the deuteron. And if you do this, indeed you get something really, really similar. We also consider short-range correlations. This happens when the two nucleons and the nucleon delta, they are very close to each other, and then there is some revulsion. So basically you have that in the pion propagator, you can split this into two terms. One that has L equal to 2 and the other with L equal to 0. So basically the short range correlations, they kill this factor. So you need to sum here a term of opposite sign. If you take into account pi and rho exchange, this comes into another coupling that is fixed to be around 0.6, and this is substitution. So we also include rho exchange, that it can be easily done by means of these substitutions, and the impulse approximation by means of evaluating these three diagrams. So at the end, we take into account pion exchange, rho exchange, correlations, and the impulse approximation in order to calculate the differential cross-section. So here are the results for the two-proton fusion reaction. And as you can see, we can reproduce very well the experimental data, except at low energies. We have considered that this process is dominated by a delta in the intermediate step. So, I mean, we are aware that there are other processes that will contribute at lower energies, but are much less important than the peak actually driven by a triangle singularity. So, since the two initial protons, they are antisymmetrical, the differential cross-section gives the same for p pi and minus p pi. So at the end, it actually depends on the square of the cosinus of theta. So we have calculated this, the angular distribution, and we have compared with the data. And as you can see here, for kinetic energies of the proton are of 570 MeV. This gives very good agreement. And when you go to high energies, we have some deficiencies for forward angles. These are the contributions of the pi, rho correlations and impulse approximations terms. And as you can see here, the pion basically dominates the interaction, while the rho exchange, it reduces the cross-section around the 2/3. It is very interesting to see from here that the correlations, they give basically nothing, and this means that L equal to 0 is negligible and L equal to 2 dominates. If we go to the spin transitions, we can see here the different contributions, and we see that the orange here is this contribution, and it really dominates, and the final cross-section actually has the shape of this. So this basically tells that probably S equal to 0 dominates, and then we build this combination of a spin, and we see that in this, indeed, this is the case, because when we calculate this, putting here a plus for the initial state, we get nothing. So this is actually a spin equal to 0. So altogether, we have dominance of L equal to 2 and a spin equal to 0 in the PP fusion. So this, well, now we go to the two-step process mechanism where you have the 2 pions in the final step. And as I said here, you have the 2 protons where this initial state is dominated by L equal to 2 and a spin equal to 0. So the parity in this reaction is positive because the 2 protons, they are antisymmetric, and this parity is transferred to the initial state. Here, the final pion, we said that when you have a triangle singularity, the particles, they are moving collinearly, and Lz is equal to 0, and you have here a p wave coupling, and then the spin of the full pi, the third component of a spin of the full pi plus d is equal to 0. So if you put these things together, then you get that here you have in the intermediate step a spin equal to 2, and third component of the p pi pp equal to 0. Then if you combine this with the L equal to 1 of the pion coupling, then this gives you that for the initial step you have 2 0 coupling to 1 0, then you can have either or 3 0 or 1 0 for the initial step. Also, you can use arguments of the antisymmetry of the initial step. So because the isospin equal to 0 wave function of neutron proton is antisymmetric, so this is symmetric, the full one has to be symmetric, antisymmetric, sorry, so this necessarily means that the spin of the initial state has to be equal to 1. So, and then again, you have that in this reaction mechanism, the total spin can be either 3 or 1. So in terms of this notation, this means that the 3D3 mode dominates the reaction. And this is actually the spin that has been given to the divarium. So we get the quantum numbers of the divarium peak. So now we go to the calculation of this reaction. So there have been trials for doing this, but this was, as I said before, the theoretical calculations, they never gave the experimental data related to the divarium. So, but now we have much more precise data on the first step, and what we do is to combine the experimental data on the first step mechanism and the second step and try to build a cross-section by means of using these two different differential cross-section, and then to see whether we get a peak that can describe the divarium. So these are the two differential cross-section for the first step, and P going to pi minus proton-proton, and then for the second step, where you have the triangle singularity, the pi plus deuteron. We do an assumption. Well, here this is the amplitude for the two-step process. This can be written in terms of a loop involving the proton, sorry, involving the two protons and the amplitudes of the two-step mechanism. we do an assumption, that is to assume that the two protons in the intermediate step, they are on shell. And then this was the approximation that it was used by Barnier. And if you do this, basically what you have to do is to keep in this propagator the imaginary part of it. But we also check whether this approximation is good or not, and we consider also off-shell effects. When we consider off-shell effects, we just substitute this factor that has come here by means of the by the two baryon loop function, which is this one. So in such a way that we can write down the differential cross-section of the full mechanisms in terms of the differential cross-section of the initial step and the amplitude of the second step. Here we do one more assumption, that is to assume that since the two pions, they are in isospin equal to 0 and the wave function has to be symmetric, L must be even, and we have a preferred direction for L equal to 0. This is, we assume that the two pions, they go together, and the energy of one pion is just the half of the energy of the two pions. And indeed, if we go to the experimental data, we see that in fact, there is a peak in the differential cross-section distribution around the threshold of the two pions. So this means that the two pions going together, this is called the Bose enhancement, it dominates. So in such a way, we can relate the cross-section of the two-step mechanism to the cross-section of the first step mechanism multiplied by the one in the second step. And from here, if we take into account that we can have intermediate step proton-proton or nucleon-nucleon, we include a factor 2. The experimental data, they actually come from nucleon-proton going to NN pi. So, and this is related by means of isospin with a 1/3. So when we do this, we get this relation. And we fit the first step and the second step to Bray-Birner. For the first step, we get two solutions, which are here. And for the second step, we get this solution. So these are the final results. So this is the blue curve shows the first step mechanism, and the one in purple, the one driven by the triangle singularity of the two proton fusion reaction. And when you combine both, you get this peak that we have multiplied it by 10 in order to see it more appreciably. And we can compare it with the peak of the divarium. So you can see here that we actually get a peak around the same position than the one of the divarium and with similar strength when we compare with experimental data. So that was for the set 1 parameters. For the set 2, we get something very similar. And this is a table where we have gathered all the results. When we consider the off-shell effects, we see that they have a very small effect. And this is this value where we say that the two pions go together close to the threshold. So this is the amount added to the threshold. And when we vary it to different values, we get similar results. So the results do not depend much on this choice. So, so we have obtained a peak with this strength. The position is around 2,340 MeV and the width around 80 MeV. And we need to compare it with one of strength 0.5 and at 2,365, but in beams of 20 MeV. So I think we think that this is enough to show that the dominant reaction mechanism of the divarium is this two-step process. So as a conclusion, we have shown that PP going to pi plus D reaction has a triangle singularity. The sequential 1 pi n production and P going to pi minus PP followed by the two proton fusion reaction offers a natural explanation of the peak, which has been so far associated to the divarium peak. And we have explained why the quantum numbers observed in the experiment are 3+. Okay, thanks. I have finished.
Yeah, okay. Thank you very much, Raquel. Yeah, so we don't have much time, but maybe for a very quick question, if there is any. And if not, you can also ask in the chat later, but let's move on to the very last contribution to this session, and it's by Peter Pauli, who is going to talk about the spin density matrix elements for lambda 1520. So,
hello, let me share my screen.
Yeah.
Okay. I hope you can see my presentation, and do you also see the cursor?
Yeah. That's fine. Okay.
Good. So, yeah, thanks for the introduction, and thanks to the organizers for giving me the chance to present my results here on the spin density matrix elements and the photo production of the lambda 1520 at GlueX. I want to briefly talk a bit about the motivation, not just for this presentation, but for GlueX in general, because I'm not too sure how familiar people are with this experiment. So the main objective for GlueX as an experiment was actually the search and study of hybrid mesons or exotic mesons. So mesons that are not simply QQ bar, but where the gluon actually contributes to the overall quantum numbers of the state. And in order to do something like this, you really need to measure a large variety of charge and neutral final states. This, of course, affects how you plan the experiments, and especially there's this assumption that if you use a photon beam, you can assume something like vector meson dominance. So your 1 - photon beam is basically like a vector meson, which has a flux tube which you can excite into these exotic hybrid mesons. So a natural way to perform this experiment is therefore by using a real photon beam. But if you want to analyze those reactions, or the reaction products rather, you're really looking for needles and haystacks. So you really need to have a very good understanding of all involved physics processes, and the first step, especially the production processes, which will then help you quite a lot in doing your analysis. So GlueX is located at the CBAF Accelerator Jefferson Lab in Virginia. And CBAF provides an electron beam with up to 12 GeV electrons. There are 4 experimental halls at Jefferson Lab. ABC are alt halls, which contain high resolution spectrometers, which perform high luminosity experiments, or class 12 and hall B. And GlueX is in this newly built annex here, which is hall D. And as I mentioned, it focuses on exotic hybrid mesons. But because we took so much data and have this extensive data sets taken with a general purpose detector, we have a huge opportunity to perform all sorts of other measurements as well. So we can measure a wide range of reactions. A few more words on the experiment itself. So I mentioned before, it's a real photon beam we use, but the accelerator provides us with electrons. So how do we get a photon beam from electrons? We use the so-called coherent Bremsstrahlung technique, where we basically have the electron beam hit a thin diamond radiator. So you can see here on the screen, the electrons are then deflected by a so-called Tiger magnet. And we can measure this electron beam after the deflection to determine the energy of those electrons. which will tell us something about the photons which are produced by this Bremsstrahlung process and which go in forward direction onto our detector. This coherent Bremsstrahlung has a very specific flux distribution, which you can see in the top left here. So what's plotted here is the photon flux versus the photon beam energy on the x-axis. You see this big peak here. We call this the enhancement in our photon spectrum. And it sits at about 9 GeV. And that's also why we sometimes refer to our photon beam as a 9 GeV photon beam, although it's a spectrum, but it has this large enhancement at 9 GeV. So that's where we focus our measurements on. Because we use a diamond as a radiator, we can adjust it just right and produce a linearly polarized photon beam. So not just photons, but linearly polarized photons. And the photon polarization is plotted below the flux spectrum. So you see it has up to 40% polarization roughly, and the polarization sits exactly where we have our enhancement. So that's very useful. The experiment itself is, well, what people often would call, I guess, a general purpose detector. So we have our liquid hydrogen target in the center of the detector, which is surrounded by drift chambers and calorimeters. The whole thing is sitting in a magnetic field so that we can measure the momentum of charged particles. And also in forward direction, we have a time of flight detector for particle identification and another calorimeter. We have quite large acceptance of about 1 to 120 degrees, but keep in mind it's a fixed target experiment, so everything is boosted forwards. So in effect, if you're in your center of mass system, you basically have 4 pi acceptance and can measure really quite a large range. Our charged particle resolution is about 1 to 3%, and for neutral particles, for photons, we have a resolution of about, well, what's shown there, 6% over square root E plus 2%. So pretty good resolution for charged and neutral particles. I want to add that since last year, we had a new addition to our experiment, which will be extremely useful for strangeness measurements. We now have a Dirk detector, so it's a detection of internally reflected shrink of light. And this really improves our pi and Kane separation up to 3 to 4 GeV. And of course, this is really useful if you want to do strangeness physics. You need to efficiently identify kaons. So as I mentioned, this is an addition that's and very recent, and we started taking data with this just last year. So the results I show today are from the period before, so basically just the GluX1 setup, but I wanted to mention this nevertheless. The Lambda 1520, just very briefly, I'm sure many people are familiar. It's UDS core content. It's a JP3 ½ state, discovered quite a long time ago in with the K- beam experiment. And there are previous measurements in photo production as well, but most of them, the vast majority, are taking much lower energies than GluX energies. There are like even recent publications, but again, just at lower energies. There's one experiment I'm aware of, SLAC in the US, which took some data at higher energies, but this was 50 years ago. So if you want to learn about this state and what it means for our physics program in GluX, we really have to do our own measurements, basically. So this is one of the many initial analyses, really, to understand the detector and the important physics processes, especially production processes that are going on in GluX. So in principle, when you think about the production process, you could think that proceeds via one of those 3 mechanisms here, some sort of S-channel production, T-channel, or U-channel production. Actually, in GluX, we assume that the dominating process at 9 GeV is this T-channel process. We have the photon coming in, like a peripheral scattering, basically with the proton targets. You produce a K+ going forward, then you have some exchange, and then you have the Lambda 1520. But although it's fairly established that this is the way the production proceeds, we really don't know much about this exchange particle here. So basically how this exchange works in reality is something we want to discover with this measurement. And to do that, we can measure spin density matrix elements. So they are basically a way to parameterize the angular distribution of the decay of the Lambda 1520, and this is directly related to the production process. So this is an event display of the reaction. So I studied the reaction gamma proton going to K plus lambda 1520 going to K plus K minus proton. It's a very nice final state experimentally because it has a large branching ratio and only 3 charged particles. So it's very accessible and good for an early physics analysis in GlueX. Well, to select this final state, we can use some basic detector timing and DDX for PID and use kinematic fitting to ensure form momentum conservation. This is basically just to select our exclusive K plus K minus proton final state because we want to do an exclusive measurement. And on the right here, you can see our invariant mass spectrum for the proton, the K minus. And you see this very nice peak here corresponding to the lambda 1520. You also see a higher excited states in this final state, which are mostly lambdas and maybe a few excited sigmas as well. But we are focusing on this peak, which is quite isolated from the rest and very, very narrow, which is good for a measurement. To remove the remaining background, we perform a sideband subtraction. So now that we have our lambda 1520 events, basically, how can we actually extract the spin density matrix elements? So I mentioned before, they parameterize the angular distribution of the lambda 1520 decay. So what we need to measure is exactly this angular distribution. So we do this in the so-called Gottfried-Jackson frame or T-channel helicity frame, where you basically boost into the rest frame of the lambda 1520 and measure then the angles of one of the particles. So in my case here, measure the angles of the K minus and the lambda 1520 rest frame. The fit function that you have your equation that's of concern is shown down here, and you see you have those 9 SDMEs in red, those rho denoted as rho, which you want to extract from your fit, and you have 3 fit parameters. 3 variables, the 2 angles of the K minus. And since we have a linearly polarized photon beam, also the polarization vector of your incoming photon beam, which you can use as well to gain some additional knowledge about some of those SDMEs. So it's quite a complicated fit function, many 3 parameters and 3 variables. So the way we extract this for this analysis is, or the way we perform our fit is by using a Markov chain Monte Carlo technique. So basically what we do is we calculate the likelihoods on an event-by-event basis and then sample this likelihood distribution. And it works very good for multidimensional problems like this. We do this in 8 bins of form momentum transfer T. And if you look at this sketch here again, this is basically what we want to measure, right? We want to uncover this production process here, the exchange mechanism, want to understand this. So it becomes apparent that binning and form momentum transfer from the photon to the K plus seems to be a natural choice of binning variable to learn about this exchange. Shown on the bottom is just an example for a specific T-bin, what the fit looks like. So the phi and the theta in the Gottfried-Jackson frame of the K minus distribution can be well described by this fit function. So let me dive into the results. Those are the results for the 9 spin density matrix elements in 8 bins of momentum transfer T. I also plotted a blue solid and a red dashed line, which are model predictions based on a Regius framework kindly provided to me by 2 theorists. And you can see that basically the agreement between the data and the model prediction is not really that good. So they get most of the science right, but in general, the description has some room for improvement. And this really shows that those measurements have the potential to really constrain the models for the future. I just want to remind you again that the previous measurements, there are no previous measurements for this energy regime, right? So this is basically their model is based on measurements taken at much lower energies and higher energies, and then they sort of try to interpolate between those two to give some prediction for the GluX energy range. And this shows that you really need some data to get this right. But when you look at those numbers, they don't really tell you much. There's no very intuitive way to think about SDMEs or what they mean or how to interpret them. So in order to get a better feeling for what our numbers actually mean, what a certain value for a rho SDME actually means, we got some help by Vincent Macchio from JPAC, who helped us to interpret those results. So basically what we're able to do now is we're able to interpret those results in terms of natural or unnatural exchange amplitudes for this exchange particle X. In this that's the wrong button, I'm sorry. In this context, the naturality refers to this value here. So if you have an exchange particle X, which has some spin parity quantum numbers JP, you can assign it a naturality based on this equation. So when you do this, you will see that vector mesons or tensor mesons, for example, are natural, while pseudoscalars or axial vector mesons are unnatural. So what you can then do is you can find combinations of SDMEs like shown here, which consists of purely natural, denoted by N, or purely unnatural, denoted by U, exchange amplitudes. What this means is if we now plot these combinations, as I've shown here, you can really try to, or you can really gain some more understanding of the data. So in the top row here, I plotted the combinations that can be related to purely natural exchange amplitudes, which means tensor or vector mesons. And then the bottom row, I plotted the combinations of SDMEs that are purely unnatural. That means pseudoscalar or axial vector exchange particles. You can really see that over the most of the T range, really natural amplitudes dominate over unnatural amplitudes. Unnatural amplitudes are mostly consistent with 0 or very small, while natural amplitudes seem to dominate this exchange. And that's now really nice because that's really something we can now understand, right? It's like not as abstract anymore as SDMEs. So basically what we could show that in the production process of lambda 1520 at higher photon energies like GluX, the exchange is really dominated by natural exchange amplitudes, while unnatural exchange amplitudes don't have that an important role to play. Since I saw that I'm the only GluX talk at this workshop, probably not very surprisingly, I also wanted to use this talk to do a little bit of a showcase of what GluX is up to in terms of other strangeness related physics. So excuse the busy slide, I tried to pack as much plots into it as possible. So basically we already have a publication on the beam asymmetry of the sigma 0, which is also concerned with the production process of the sigma. And also similar to the case of the lambda 1520, the sigma seems to have a production process that's dominated by natural exchange amplitudes. If that's something that's general to all strange baryons, I do not know, but we certainly saw it that in our first two measurements of the kind, the natural amplitudes seem to dominate. We also perform measurements of lambda anti-lambda. We see very nice data sets of many thousand events of lambda anti-lambda, which is now currently under analysis. Also looking at cascade anti-cascade, but this is still preliminary. Don't have anything to show yet. We also look at other excited cascades, so ground state cascades and excited cascades, some of which haven't been seen in photo production yet. So that's something GluX can look at. That's also another excited cascade which we see in our data. There are some ongoing analyses around the lambda 1405, which I know is of great interest for this workshop, but unfortunately I'm not allowed to show any of the plots yet. But stay tuned, there are analyses coming out of this data set very soon. Especially I think they're trying to measure not just cross-section, but also the line shape of the 1405. It's one of the goals to measure. And Also, as I mentioned before, GlueX2 started taking data with a new dirt detector last year. So this is going to stay in there for, I think, about 3 years. So we have 3 years of data taking with this dirt detector, which will generate a data set that's much larger than GlueX1, which is great for a lot of strangeness physics. Again, most of the focus will be on exotics, exotic hybrid mesons with STRANGENess, but also a lot of other strangeness physics is going to come out of this. And although it's not directly GlueX as an experiment, but it's using the GlueX detector, there was a proposal approved by the Program Advisory Committee at Jefferson Lab for a K-long facility. So there's going to be an experiment that produces a K-long beam, which will then use the GlueX detector to detect the events. And of course, the K-long beam has a lot of very interesting possibilities for future measurements. But this is not likely to run before 2026 or so. So still a few years to go. But yeah, there's a lot of exciting physics coming out of GlueX over the next 10 years or so, I think. That's my summary. I presented the first measurement of the lambda 1520 SDMEs at GlueX energies. And actually, those are the first measurement of polarized SDMEs in general, because we have this great linearly polarized photon beam, which will help us a lot to understand those production mechanisms. I've shown that the production is dominated by natural exchange amplitudes, which is something we saw in a previous publication with hyperons as well. The paper is currently under collaboration review. So as you've seen, maybe there was always like a tiny preliminary tag on all the data. But hopefully over the next couple weeks, I can finally post it to the archive. And just as a sort of advertisement, please keep GlueX in mind. There's lots of exciting strangeness related physics coming out of the next couple months and years, especially with the new GlueX2 setup, which will open a new door for us, I think, in terms of strangeness physics. Thank you.
Okay, thank you very much, Peter. So yeah, there is time for questions. Yeah. I don't see any, so maybe I was just interested, you have mentioned the MC algorithms, and if you could be more particular in what kind of algorithm did you use to?
You mean on a?
Yeah, you mentioned the Markov chain Monte Carlo.
Yeah, there you go. Yeah, so on a very technical level, we use the roostats implementation to our analysis and the root framework.
Okay.
I also tried out various other algorithms, which all agreed and the result.
Yeah.
No, yeah, sorry.
No, I was just attracted that you've mentioned that it acts around 4 multi-dimensional problems, but yeah, in my case, whenever I try to apply it for really multi-parameter optimizations, then I failed miserably. So.
Okay, we had a lot of problems fitting this with a standard minuet fit, especially if you want to get good uncertainties for your parameters. You need to do lots of bootstrapping and the likes. So we found that using directly sampling the likelihood distribution with this MCMC method gave us very, very reliable uncertainties and very good convergence. Basically, we found the proper fit results very fast. If you're interested in having a chat about this, feel free to send me an email. We can talk about this later.
Okay, thanks.
There are really good implementations also for Python if you're not too keen to use the root framework.
Yeah, this is what I usually try to use. Usually some Python package either to multi-nest or something like this.
Really, yeah, EMCEE. It's called. I just call this. That's really good framework as well.
Yeah, I know as well. Yeah. Okay. Thank you. So, any more questions, comments? Yeah. If not, then I don't know if maybe Christian has some more announcement, or Catalina. I don't really have anything.
I just thank very much all the speakers of the two sessions of today. It was really, really very interesting. And we meet tomorrow. The Italian time is 9. And the day of tomorrow, as Catalina told us, will be dedicated to celebrate the career and the contributions of Professor Butzek to this physics and nothing. Good afternoon to European colleagues, good evening to the Japanese colleagues,